Hello, I'm Dr. Ala Kamerdiner. Welcome to Discrete-event simulation. This is Lecture 12, Modeling Basic Operations and Inputs. I will talk about input analysis and Arena Input Analyzer. So when we talk about input analysis, we actually talk about specifying model parameters and distributions. When we did things before, we focused more on structural modeling. And that's where we looked at logical aspects of our models. We figured what our entities were, what resources to use, how the entity moves, so knew the paths of the entities through the model. Now, what we will be talking about is quantitative modeling. So in comparison to structural modeling, it does serve as an important part of modeling, but it actually does not deal with logical aspects that structural modeling dealt with. Instead, it looks at numerical and distributional specifications. So the quantitative modeling focuses on distributional specifications and does a numerical analysis to support your assumptions. And like structural modeling, quantitative modeling needs to observe systems operations, and it also needs data if possible. When we talk about different types of inputs, we distinguish between deterministic and random inputs. Deterministic inputs are non-random, they have fixed values. Example is number of units of resource. Sometimes entity transfer time can also be deterministic. Sometimes when the arrivals are scheduled, then inter-arrival times could be deterministic, or if processing is strictly scheduled, then the processing times might be deterministic, but that depends. We could also have random inputs, and random inputs, also known as stochastic, and they model a value as a distribution, so that will allow us to draw or generate values, and these values that are generated from this random distribution will be used to drive the simulation. And so example of the random inputs are transfer, inter-arrivals, and processing times. So as you can see, right, we also mentioned earlier that deterministic input could be when we have the inter-arrival or processing times as scheduled. Well, very often though, these arrivals or processing is not scheduled, and they actually vary, and so in that case we have random inter-arrivals, processing, or transfer times. So a big question is what distribution we should use, what type of distributional parameters we're going to choose. So in order to do that, we need to analyze data and understand through the input analysis of what distribution to choose and what parameters for that distribution we need to specify. So when we use these random parameters in our simulation model, it causes simulation output to be random. And so it's very important to later to also know how to analyze the random output. But right now we focus on random inputs, and we assume that some of the inputs might be random. So again, it's very important not just assume the randomness away and decide that something is deterministic, but make sure that that's actually a valid assumption. So even though it might be more straightforward or easier in terms of modeling to assume our entity transfer times are deterministic, but if we study the actual data for the system and we determine that they're not deterministic and there's actually significant fluctuation in those times, then we shouldn't assume the randomness away, and we should model them as random. So as I mentioned, right, in order to understand what kind of parameters we need to be using, we need to make those assumptions based on analysis of input data. So in order to to analyze the data, we need first to collect the data. So collection of the data is generally hard, expensive, and frustrating. It can also take a lot of time. And the difficulty in terms of data collection can come from different sources. It might be that the system might not even exist yet, and you're trying to design a new system. In that case, right, you might not be able to collect the data from the system. The data that are available might be available on different type of things that what you're going to model. So when the data are available on the wrong things, right, they might have to change the model according to what's available. Sometimes you might have incomplete or dirty data. So in that case, right, example is you collected some of the data, but some of the things were not recorded, or there were some mistakes when recording the data, right? That would result in your data being incomplete or dirty. Another issue which might come as a surprise to you is when you have too much data. And another thing that you need to take into consideration when thinking about how to collect the data is sensitivity of outputs to uncertainty in inputs. It's also important to match model detail to the quality of the data. And the cost of data collection should also be budgeted in your project. When collecting the data, it's important to capture variability in the data, and that will support your model validity. And because of that, there's a rule, right, that we can summarize as garbage in, garbage out. If your collected data, right, were collected in a very sloppy way, you would get some incomplete, dirty data, or data that are collected on the wrong things, or maybe data just not available and you're assuming things away, right? If you put those things in your model is not going to be valid, so your output from the model will also not be correct. It will be wrong. And that's why we say garbage in, garbage out. So when using the data, you need to use the data directly. You can use the data directly in simulation, but that would mean that you would be reading actual observed values and then drive your model based on those observed values. So you would be just processing the data that you actually observed for intervals, service times, or part times. And this is actually possible in Arena when you use the read-write module. For more information, you can look into Model 10.2 from the Arena textbook. In this case, when you use data, observed data directly in a simulation, all values will probably be legal and realistic, but you can never go outside of your observed data. And that's a disadvantage as well, because you want to see, right, that's just maybe a single or several observations, but they don't describe enough, of some other possibilities. So you might not have enough data for long or many runs. And it also is computationally slow because you have to actually read disk files as you do the simulation. So another approach to using the data is, instead of using the data directly and reading the observed data in your model, the other way to do it is to fit probability distribution to data to determine what is the probability distribution that's likely generated the data. Then you can draw or generate synthetic observations from this distribution to use it in your simulation model. And that's what we've done, right? So far, we kind of use the probability distribution and use that to drive our models. So in that case, we can actually go beyond the observed data, and that actually is a double-edged sword, and it has some good properties and some bad features. So it might not get a good fit of the data, and then that would be that would be generating some concerns in terms of validity of your model. So to do some of the fitting of the distributions, we could actually use this tool in Arena known as an input analyzer. So we will assume that we have simple data. So the assumption is when we talk about simple data is that observations are independent and identically distributed, and those observations come from actual physical system. And we want to select or fit a probability distribution for use in generating inputs for simulation model. So Arena Input Analyzer is a separate application, but you can also reach it via Tools menu in Arena, and I'll demonstrate that. And what it does, it allows us to fit distributions and also gives valid Arena expressions for generation so that you can directly paste it into your simulation model. So let me go ahead and open the Arena Input Analyzer and demonstrate to you some of its functionality. So here I open Arena, and I can open Input Analyzer from Arena. I just click on the tools, and then in the tools I select Input Analyzer, and that loads Input Analyzer. So now the Input Analyzer has loaded, and the next thing I can do is I can start a new file to do my analysis in. So I can either press this button New here, or I can go File and then New, and it opens a new Input Analyzer file. And here to analyze something I need a data file, which I can either use an existing data file or I can generate some data. So let me go ahead and open an existing data file. So I'm going to go ahead and do File, and then I don't say when I open the data file, I don't go File Open. This is to open the Input Analyzer file. I go to Data File and then Use Existing. And so to open the data file, I go Data File, under File, and then Use Existing, and I click Use Existing, and then I go to my data, and right away it asks me for some distribution files, but I can also look at all files when I select here, or just say text files. So I'm going to go ahead and select text files, and I can open this text file here. And so I'm going to click on this text file, and I say Open. And so now right away it loads my data file and then creates the histogram of the file. And then in the second pane, it actually has the information about the data and also information about the histogram that was generated. So let me show you how the file actually looks. So this is actually how my files looks, right? So if you look at this file, right, this is what this file contains. It contains some integer values. And so this is my data. And here it tells me about what kind of data it has, right? It says it contains 10,000 data points, and it has this minimum data value and the maximum data value, so it's between 1 and 4. It also tells me about the sample mean and sample standard deviation, and this is a histogram range that was generated. So what I can also do here is I can fit the distribution to the data, and I can click here to fit all, or I can click here and say fit and then select a specific distribution, or I can fit all of them. So in this case, I can click fit all, and also when you can, if you wanted to use existing data file, you can also use existing data file here, right? Instead of just doing file data file and then use existing. So now let me demonstrate, right, if I want to fit all, what's going to happen. So I'm going to fit, and keep in mind, I showed you the actual file, and it has integers, right, from 1 to 4. And so when I fit all, what it actually generated is it generated this distribution summary, and it selected a normal as my distribution fit, right? Of course, I know that normal is not a good distribution fit because I know that my file only contains integers, and these integers are of specific range, right? So I kind of know this is not really a good distribution. So notice here there is also information below about the square fit and the square error. The square error is rather small, and it selected this because it's the smallest error out of all the other ones. But when I look at the distribution fit, the distribution fit information is shown here. An important part about the distribution fit here is the corresponding p-value. And the p-value is very small, right? It's smaller than this very small value of 0.005. And so I know, because my p-value is extremely small, that it's not a good fit. And I'll discuss with you later on why that's the case. So even though the normal distribution has the smaller square error, it actually doesn't have a good p-value. The p-value is extremely small. So that tells me it's not a good fit because the p-value is too small. A small square error is good, but it's not, in this case, it's not the most important part. The most important part is the p-value, which determines of how good the fit is. And so the fit is not good, even though it's a small. And so if I click here, it actually, right, so I click here, it says fit all summary. So this fit all summary is what I can do. So again, right, I fit all possible distributions that are listed here, right? And so now when I click on fit all summary, it tells me about the square errors. So as you can see, the normal distribution has a smaller square error out of all the distributions that were fit. And if you look at this, right, it fit these continuous distribution: normal, beta, Weibull, gamma, Erlang, long normal, triangular, Poisson, exponential, and uniform distributions. It did not fit, however, when we did the fit, it did not fit the empirical distribution. So what I want to do is fit the empirical distribution, because that would be a discrete, would fit better to discrete data. So I'm going to fit empirical. And now that I click on fit empirical, you notice that this input here has changed. And it also shows not only histogram, but it also shows the distribution function. So the histogram is actually an approximation for the probability mass function for a discrete variable. So here when I do empirical, it tells me it's either continuous or discrete. And so I know, because I looked at my data, I know my data has only integers, so I choose the discrete distribution here, right? And then here, these are some of the values, right, that it fit. So I could actually copy this expression here and use it directly, simply copy it, right, by saying copy, and use it directly in my model. So again, it has the data value, right, and the histogram range. If I wanted to do some of the changes for my histogram, right, I could actually click here in terms of the parameters, options, parameters, and then the histogram. And there I could change my low value and my high value. So let's say, I want to change my low value to 1 and my high value to 4. And then I'm going to have 4 different intervals. Let's see if it changes, right? So now it from 0 to 99, then, right, so it has a different, right, it generates a slightly different expression. So another thing I could do, right, is I can change, when I do the data fit, right, I can change different tests. So right now, only have output summary files and auto data translation. I could include the Kolmogorov-Smirnov test. So this KS test means Kolmogorov-Smirnov test. So if I wanted to, I could include it when I do fit all. It then will include that as well. So for now, I'm going to finish this demonstration and go back and discuss a few more important things about fitting data. So here I'm going to review how we use the input data analyzer. And what the fitting really is basically deciding on a distribution form and also estimating its parameters, right? And distribution form is what type of distribution it is. Is it exponential, gamma, empirical, and some other distribution possibly? So there are several different methods that exist on how to estimate distribution, right, or fit data to distribution. And these include maximum likelihood method, moment matching method, and least squares estimation method. So what we're doing when we're fitting, we're also assessing goodness of the fit using the statistical hypothesis testing. And in that case, we're looking at the hypothesis H0 that assumes that we fit a distribution, that the fitted distribution adequately represents the data, versus the H1, which is an alternative, that the fitted distribution is not a good match for the data. And in that case, we get p-value for the test, right? So you saw when I demonstrated in Arena, it generated the corresponding p-value. So p-value for the test is very important because it tells us how good our fit is for data. And the small p-value represents a very poor fit. And so when we fit, right, we can fit theoretical versus empirical distribution. And I showed you that for the data that we looked at, the empirical distribution was actually better than the theoretical distribution, but that's not always the case. It also, we can look at continuous and discrete data, right? And I had the discrete data, so I wanted to use a discrete distribution, right? And then even when we do the empirical, it gives us a choice of whether it's going to be a continuous distribution or a discrete distribution. And then we also have the best fit among several distributions. And the best fit is often decided based on a smallest square error. So to do the fitting, right, is basically we follow this procedure. So you can create data file, and that's just a plain ASCII text. And then the values are separated by white spaces, can be blank tabs, line feeds, right? So otherwise, it's a pretty free format in terms of creating data files that you can be using. And so we open the data file from input analyzer, and then we used existing data. And we got the histogram and summary of the data when I demonstrated that. And to see the data file, we could also click Windows Input Data. And we can generate a fake file, right, to play around. So I can show you in a second how to generate the file in Input Analyzer. So here I'm back to my Input Analyzer. I'm going to create a new input file in where I'm going to analyze the data. And here I can just click on File and then Data File and then Generate New. And that generates my data. I could, for example, generate some normally distributed data. And we know that let's say our mean is going to be 0 and our standard deviation is 1, so it's a standard normal distribution. And you can choose whether to allow the negative values. And this is a number of data points, so let's say I'm just going to have a smaller number of data points, and this is my file name. So it didn't want me to use the negative a 0 mean. So let's say we're going to have our distribution centered around 1. So now, right, let's see what we got. So you see here we generated 100 coins, right? And these are the minimum and maximum values. This is our simple mean. So actually the mean, right, is slightly different. What it estimated from the actual, right, we generated it from 1. But when we fit the summary, because remember, this is the part which shows the data summary. So when it fitted the generated data, it actually, right, the estimate is slightly different from the actual mean that we generated from. Right, remember this is a sample mean that's estimated from these 100 points, and this is a sample standard deviation that's estimated from these points. And there's some information on the histogram summary, and again I can fit all and see what fits the best. And to our surprise, right, it actually fits the best seems to be the weighable, even though we know we generated these data from the normal. So why did it do that? And let's see how good is the fit. Apparently that's a good fit, right? The weighable is a good fit because the p-value is large, right? And the square error is the smallest. If we click here on fit all summary, right, the weighable appears just slightly smaller square errors than normal. So why does it happen? This is simply because, right, we only had 100 points, right, and then we estimated this distribution, so weighable turned out, right, it overfitted. We kind of overfitted those data with weighable. And so if I know the data are more likely to have come from normal, I can actually fit normal distribution here by clicking fit and then selecting normal. And now I changed my distribution summary because I didn't fit all, I only fit normal. So now this is my square error for the normal, and also the corresponding value, right, the p-value is very important. It determines whether my fit was good, right? So it tells me here for both cases, for chi-square test and for Kolmogorov-Smirnov test, both times the p-value are rather large, right? So here, what it means that we cannot reject the hypothesis that the data came from this distribution. Of course, as you can see, the normal distribution has the parameters of the distribution is also slightly away from what the actual distribution was, which was normal with parameters 1, 1. But it's close enough, so what we could do, right, is we can then copy this expression here and use that expression in our model in ARENA. So now when I showed you how we can generate new file and also how we analyze it, let me review the fit menu. So the fit menu that we used, right, fit distribution, it also does goodness of fit test, and it fits a specific distribution form and plots density over histogram for your visual test that you saw there on top, and it gives exact expressions that we were able to copy, and it can include offset depending on distribution. As you saw it in weighable, weighable distribution included offset of 2. We had 2 plus the weighable, and that was the best fit because it had the smallest square error. So again, the fit menu fits specific distribution form, and the two tests that you saw is chi-square test and also Kolmogorov-Smirnov test. So I want to stress again that the most important part of these tests is the p-value. It's always between 0 and 1, and what it represents the probability of getting a data set that is more inconsistent with the fitted distribution than the data set that you actually have, if fitted distribution is truly the truth. And so in that case, right, you can see, right, the small p-value, which basically is less than 0.05, is a poor fit. So you should try a different distribution, right? Or you might want to give up and try to collect another set of data to see maybe this is just a bad data. So the fit menu that we used, right, we also used fit all, or we clicked on that button, and it returned us the minimum square error for distribution. And the square error is actually, the good square error is a small square error, right? But the small p-value is bad. So the square error is a sum of square discrepancies between histogram frequencies and the fitted distribution frequencies. And it can depend on the histogram intervals that we've chosen, and different intervals can also lead to different best distribution. So even with a very small square error, we could still get a poor fit. I already showed you in the first demonstration. So it's very important to first check the p-value. And you can also see all distributions ranked, right, by clicking window fit all summary, or what we did is we clicked that button here that is kind of shown as grayed out, but after you fit all, right, it can show you this button. So again, right, we also use the empirical distribution fitting by going fit and then empirical, and that interprets the result as discrete or continuous distribution. For the discrete, you get the pairs that represent cumulative probability and the value, and for continuous, ARENA will just interpolate within the data range. So empirical distribution can be used when theoretical distributions fit poorly or intentionally, right? When we actually know, like in our example, we knew that it's a poor fit, but we also knew that we wanted discrete points. So in both cases, right, it was true, we wanted to use empirical distribution to create the expression for the discrete distribution, but we also knew that theoretical distributions fit poorly, and that's what I showed you in the first demonstration. So there are several issues in fitting input distributions. First of all, it's not exact science, right? So there's no right answer. And so you always need to consider theoretical versus empirical. You need to consider the range of the distribution. If you have the infinite range in both ways, like we have typically in normal, that could actually create some potential problems. You also need to consider the range of distribution, for example, positive, right? If you talk about the times, then the positive might be a good range, so you could use exponential or gamma. For example, for intervals, we often use exponential. Also need to consider the range in terms of whether it's bounded. Uniform, right, or beta have bounded range, right? So depending on what kind of range, you might select a different type of distributions. So another thing you want to consider is ease of parameter manipulation and how it affects means and variances. And so it's always a good thing to do some sensitivity analysis when looking at the inputs of the model. Another thing that you want to take into account is outliers and multi-model data. So you may need to split data set, and there's more details about that in the textbook on ARENA. And sometimes you might have to happen no data at all, right? And it actually happens more often than you'd like. So there's no really good solution in that case, but there are some possibly bad options. You might want to interview experts that know the system and try to find some minimum maximum values that they observed and try to use a uniform distribution, right? It's still better than no data at all, or average percentage of absolute error. And again, do the uniform. You can look at minimum, mode, and maximum and select the triangular. So again, mode can be different from the mean, so that allows us symmetry. For intervals, you can use them as, or model them as independent and stationary. And so in that case, for intervals, exponential is often the case. But you still need to figure out what kind of value you would use for mean. And then the number of random events in an interval, right? If you have this kind of situation, the Poisson distribution might often be an answer. And if you have the sum of independent pieces, right, then you could possibly use a normal distribution, but you need to be careful about the left tail, which allows for negative values, because sometimes that's not the case, especially if you're working with the times. You don't want to have a left tail, because having a negative time is actually invalid. And product of independent pieces, if you have that kind of situation, then the log normal distribution is probably the case that you want to use in your simulation model. So again, I want to caution you about using normal distribution, because even though you're probably the most familiar with this type of distribution, and everybody knows about normal bell curve because it's used widely in statistics, it might not be appropriate for simulation, right? You need to be really careful whether you can use it because it has infinite tails in both directions. And more importantly, it has infinite left tail. So you could get generated negative values if you have very many values that you're going to generate. You might actually get a negative value there, right? So what might happen is you have many input qualities like time durations, right? You really need to have it positive because negative time does not make any sense. So Arena truncates the negatives to 0. So sometimes the 0 time also doesn't really make much sense, so you gotta be careful. So if mu is big to standard relative to standard deviation, then the probability that you generate a negative value is small, but it still can happen. So if you want to look more into that, I recommend that you look into model 4.5 from the book. So the big lesson from this whole talk is that you should avoid normal distribution as your input distribution. Another thing I wanted to talk about is non-stationary arrival processes. And events such as arrivals can actually have different inter-arrival rate. So the rate of arrivals could vary over time. And you might have noticed that if you go during a lunchtime to a fast food restaurant, it's extremely busy, but it might not be as busy some other time. You could have rush hour traffic in the cities, right? So you can see that the arrivals, the rate of arrivals is very different during those times. So it might be critical to model non-stationarity so that you have a very valid model, because if you don't have a valid model and you model everything stationary, then it will be this garbage in, garbage out situation. So you might need to focus on the peaks. You can't just ignore the peaks, and then the values can mask important behavior as well. So you can't really miss the rush hours, right? Because that's different model if you don't introduce these rush hours into your model. So a good model in that case, when you have the rate of events vary over time, is to use this non-stationary Poisson process. And there's often two issues that arise when you want to model non-stationary arrivals: how to specify or estimate the rate function, and also how to generate from it properly during simulation. So there's actually several ways to estimate rate function, and we'll just do piecewise constants. We also estimate rate function as piecewise constant by following the following procedure. We divide time frame of simulation into sub-intervals of time over which you think that the rate is fairly flat. And then we compute observed rate within each subinterval. And in Arena, you must convert to expected number of arrivals per hour on subintervals that need not to be of 1 hour length. So the important part is to remember that you're using the expected number of arrivals per hour, right? But your subintervals might actually be smaller or larger than an hour, like 15 minutes or maybe 2 hours. So if you want expected 45 arrivals in a half hour, you need to specify a rate of 90 per hour. And there's more in terms of the example in the model 5.2, and we'll discuss it later when we discuss chapter 5. Another important issue is multivariate and correlated inputs. We usually assume that all generated random observations and simulations are independent. Also, they might come from possibly different distributions, but that might not always be the case for all models. So you need to be careful about understanding whether your inputs are correlated so that you can construct a valid model So a difficult part requires long processing in both prep and sealer operations, for example, and that would be a positive correlation. So ignoring such relations, right, can actually create an invalid model. So you can see more information in the text. So now you're prepared for Lab 5A, so you could start individual work on Lab 5A.